Gentlemen, today we're going to be discussing a proof of the Intermediate Value Theorem and also the Boundedness Theorem. So I welcome you to another installment in the noble pursuit of mathematical clarity, mathematical rigor. I haven't done a calculus video in recent weeks, so I figured we'd update the playlist a little bit. So we're going to revisit a foundational result of the calculus. We'll start you off with the Intermediate Value Theorem. It's really an inevitable theorem. It's immaculately structured. So it's going to be sort of as a way to show how to prove that. So it's not math for the, as I always say, this is not for the dabbling dilettante or the algorithmic adolescent who is raised on apps and auto-completion. This is mathematics for the classically trained mind, or those of you who want to be trained in the classics. It is for those who understand that intellectual discipline is not merely a relic of the past, as I was recently told by some idiots, but it's a standard to be upheld without apology. We stand for the truth without apology. Let the moderns, or whatever they want to call themselves, create the chaos and their so-called self-expression. And here we pursue truth, order, continuity. And that is what we're going to see today. All right, so hopefully you could see on the board now, or on the screen, whatever you want to call it. We're going to proceed to prove the Intermediate Value Theorem. And here we have the case where f of a is less than f of b. Now, of course, you have the degenerate inverse case. F of a would be greater than f of b. You can, with minimal effort, you can show it mutatis mutandis. It's really a trivial exercise, and left appropriately if you want to do it that way. But we're going to limit ourselves in this case to this for the sake of time. So we have here a situation. We can call it y, the function y, whatever, or the variable. But we're going to say f of a is less than y and is less than f of b. So we really, what we desire here is a point. We need to have a point. We demand a point. We could call the point C of a and b, where f of c is going to equal y. So we have a set here that's really well defined, the set U. And think of U as it's really well behaved. It's a really good set here. It respects boundaries, unlike some people today. Now, what we see here is, if we say that f of a is less than y, then we would say the set U is not empty. Obviously, because a is an element of U. And like any collection properly fenced in, we would say is bounded above. So in other words, it has a supremum, a least upper bound, a natural leader, if you will. And we can call this C equals the supremum of U. But then we have to establish that f of c is going to equal y. So let's try to do this gracefully as much as we can. The first thing to take into consideration is a claim. And I try to type in everything, but apparently it didn't work out the way I wanted, so I'm just going to write it out. But the claim that we need to make, the first claim is, what if we said that C is not equal to A? Like C is not equal to A. If you suppose otherwise, you have an absurdity. So in this case, we have to choose an epsilon that is greater than 0 for this claim. And of course, f of a has to be less than y minus epsilon. And that has to be less than y. Now we could, in this case, we could take epsilon as y minus f of a over 2. I mean, it's a pretty good choice here. You can't really bungle this. But if we talk about continuity at A, that means that there exists a delta greater than 0 And what can we say about that? Well, if there exists a delta that is greater than 0, such that for all x, as an element of A, and we could write it out as a plus a comma plus a plus delta. So we have, in this case, f of x is going to be less than y. So x is an element of u. So the entire interval here, which is, so we would have we start at a, so the entire interval has to be a subset of u. And this forces the supremum, C, to be at least a plus delta. And if that's the case, then therefore C has to be greater than A. So now we can automatically discard, if we can call it a heresy, that C equals A. Our next point is to show that our next claim that C does not equal B. It's a parallel argument. So here we could choose epsilon as greater than 0. And from here, we need y to be less than y plus epsilon. And that has to be less than f of b. And what we see here is really it's really a mere morsel of continuity. This really grants us a delta that is greater than 0. So now any x that is an element of b minus delta and b has to satisfy f of x being greater than y. Remember, x here cannot be uh, an element of u, right? So make sure we put that in. So that means that the set U cannot reach, if we may use that term, cannot reach B. And that means that C is less than B. The endpoint B here, it really remains aloof. So that's something to keep in mind. Now, if you have A is less than C, which is less than B, if we have this, then we can let Z equal f of C. And our aim here is to demonstrate, to show that Z equals Y. So we can proceed by contradiction. We can wield logic as a saber. So if Z is less than Y, then there exists, we could say, some epsilon greater than 0 such that Z plus epsilon is less than Y. So we assume here there exists a neighborhood. So we pick x equals c prime. I was able to type it out now, thankfully, so that we don't take up too much time. And now it's an element of c plus delta, and f of c prime is less than y. So c prime would be, by that argument, we would be saying that c prime is an element of u. It's a tragic contradiction because c was the least upper bound, and you cannot be both leader and follower. Now, if z is greater than y, then we could say z minus epsilon is greater than y for some positive epsilon. And we have a symmetric argument, and it gives us a c prime being an element of c minus delta comma c, and we have f of c prime being greater than y. So that means c prime would not be an element of u, but yet we know c prime is less than c, and c prime an upper bound. That's a contradiction. Cannot have contradictions. So we emerge from the fray, f of c equals y, and it's a statement. It's an indubitable statement. QED. And this concludes this proof, and we have our theorem. Let us now look at the next theorem that we have. Now we have to discuss the next one, which is the boundedness theorem. And really what it says is that if you suppose f is continuous we have a closed interval here, then we have to think that there exists some value, um, let's just call it m. There exists some value m as an element of the real numbers, of course. We can say such that f of c is less than or equal to m, and if that's the case, this has to be true for all c that for all c as an element of a and b of the closed interval. That is, m has to be an upper bound for f on the interval. So how do we go about proving this? Well, we can proceed to identify the precise moment at which we have a defenseless function here in a way. Might the function f might first leap headlong into the abyss of unboundedness. And we have to begin, as any rational mind would. Let's begin at a point, x equals a, and we can proceed cautiously rightward. Almost like when a gentleman has to wade through a sea of barbarians, seeking the frontier where bounded behavior has to meet the howling chaos of the infinite. Now, if we talk about an interval, let's say a, let's talk about a closed interval here. How can I write this out? If we begin from that perspective, you have here a singleton, if there ever was one. And f is clearly bounded because we're just evaluating it at a, right? And f of a, in this case, obliges us by providing a perfectly respectable upper bound. There's no surprise here. The function is not misbehaving yet. It's a well-behaved function. But if we define the set, let's define a set as the set D is going to be a closed interval. X is an element of A and B. And we're going to say that it's bounded. Let's see if I can fit it in here. Well, hopefully you will. We're going to say bounded. So if you observe this, you can note that it's a collection of all those points up to which the function has managed to, it maintains its behavior, it maintains its decorum. So we have here a subset of this closed interval, AB. So D is certainly bounded, and this concept of being bounded is perhaps foreign to the average engineer, but it's comforting to us in pure mathematics. So we invoke the completeness of R, of the real numbers, which is what we're dealing with. We know that D has to possess a least upper bound. So we can christen the bound as, we could just say D equals the supremum, sup, we talked about that, of D. And if that, it follows then that for every C in the interval, if we have an interval such as AD, the image that we could talk about, in this case would be the image of F in the closed interval A and C, is bounded. In other words, the function has behaved itself up to the brink of D. And we can first banish any lingering doubt that D equals A. So we said that F is continuous at A. So we use our epsilon delta machinery. And it's so routinely misunderstood by our more practically, perhaps we can call them that, I'm being kind, inclined cousins. But it tells us that for any epsilon that is greater than 0, we may select, as we said, a delta that is greater than 0. So really what we have is a function. We can label it as follows. We can start with a and a plus delta. And we're going to say that that is a subset, of course, of f of a. And hopefully I have room here, minus epsilon. But let me see if I can rewrite it in a different way so that I have more room. Because I wanted to add to this f of a, we need f of a plus epsilon as well. All right. So what this means is that a plus delta is an element of D. And so D has to be greater than or equal to a plus delta, right? So if we write it out, we would have a plus delta as an element of D. And D is greater than or equal to a plus delta. And we have to remember also, excuse me, that that's going to be greater than A as well. So it's a small, elegant step, but it would perhaps flummox anyone whose idea of a limit is how far a beam can bend before snapping. Now, if, let's say that D did not equal B, so again, we have to wield the mighty sword of continuity. And this time at the point D, we can use an identity. The limit as x approaches D of f of x and we could say that that's equal to f of D. And with this, we have the existence of a delta that is great. If delta is greater than 0, and then we could just write it as, we could do 0 is less than or equal to the absolute value of x minus D. We should say less than or equal to here. So we have less than or equal to the value of x minus D, the absolute value, and that's going to be less than delta. And if that's the case, then the absolute value of f of x minus f of D we could say that that's less than epsilon. So I was able to type it now. Hopefully you could see it clearer than my handwriting. But basically, we have here, you can choose a delta that's small enough on this interval. Now, as you can see, the first term is tame. It has to lie snugly, of course, within AB. Can't have unruly endpoints. But the first term is tame, right? Because D minus delta being less is less than D. And the second term is tightly corralled within the interval. We have the interval f of d minus epsilon and f of d plus epsilon there. So all of a and d plus delta has to lie within d, within the set, which of course brazenly contradicts the fact that d is the least upper bound. So unless the real number line has begun to lie to us, and we know mathematics is never a lie, it's always the truth, this cannot be. And so ergo, we conclude that d is equal to b. And finally, we can add with the dignity and the rigor that is befitting of our discipline, we can examine the endpoint b. We can talk about the continuity of f at b. And it assures us that the limit of f of x, as the limit of as x approaches b of the function is equal to f of b. And so if you take a delta that's small enough such that a is less than b minus delta, you're going to get terms that are what we call comfortably bounded. The first is the virtue of our findings here, the earlier findings, and the second by virtue of we have a continuity cage around f of b. So the entire image is bounded. So there's no, really there you have it. I mean, there's no simulations, there's no hand waving, there's no appeal to empirical nonsense. It's just pure logic here, wielded with precision. And really, when you think of a complete proof delivered delivered in an elegant way, you can come up with a lot of the mathematical laws. So I'm going to actually write it out for you, what I was saying earlier, so that you can kind of see the proof of it, the symbolic notation. And so this is what I was referring to symbolically. So have a good look at it. And pretty much from this, what I'm trying to say is if you take a delta that's small enough that basically A would have to be less than B minus delta, you would complete the proof there. You would have a union in the set. You would have F A minus A and B minus delta, also B minus delta and B. So that's why we said that those terms are comfortably, if we may use it, bounded. So I hope that this was helpful to you all. If it was, please continue to subscribe to the channel. This week, like I said, I'm continuing to post as many videos related to mathematics as possible. It's a lot of work, but it's all worth it. And I'm glad that I have so many subscribers that care about the truth. This channel should be all about truth, all about pure mathematics done in a rigorous way. Thank you all, and please stay tuned for other videos.